Okay, so today is November, keep me honest guys, but it's November 14th, 2018. This is ECE 3030, basically semiconductor device physics, and we're preparing for our second midterm, which is going to be on p-n junctions. And let me start here. Depletion regions, p-n junctions. So we're going to go from junctions all the way, this exam will cover all the way from junctions to applications of junctions. So this will include metal semiconductor junctions and hetero junctions, right? And everything in between. Just to remind, Stefan.
Does that mean like the photodiodes and stuff will not be on here?
Yeah, that's an application. Yeah, so that's on there.
Oh, yeah.
Yeah. Just to remind everybody of the game rules, it's just like the first midterm, which means your calculators, you can take your batteries out and let them sit on the side because you're not going to need them. It's an essay-based. It's going to be thoughtful and drilling down to the cause and effect relationships, the rate-limiting steps. I mean, really, dissecting the way an engineer thinks about how these things work and what makes them tick. I'm trying to mold you into future engineers. And then now what I'm going to do is try and very staccato quickly go through the slides, making some commentaries as I go through of hot point items. You can stop me as I go through, and then after I get through the two slide decks, I will open up the floor to questions, and I'll try to stay here almost as long as I can until Macy's closes, because there's a sale today, and I got to get over to Macy's afterwards. So if that's okay, I'm going to continue here. So in the midterm one, we talked about all the fundamental, foundational things of what carriers are, how you put them in, they say through diffusion and so forth, and how you're going to get a free carrier concentration from the carriers jumping from the donor level or acceptor level, so we can create free charge where we need it, and so forth. We can manipulate that. Now we put two and two together, and we make p-n junctions, and then we try to discern why is there rectification. Okay, remember I challenged you on the very first lecture day of what rectification is, and so now we're trying to utilize that. So, in a nutshell, it starts with this. This is probably one of the more important diagrams here. Make this full screen. How do I get rid of this? Does anybody know how to get rid of that?
There's an arrow right there.
Yeah. The arrow?
Next to organized pages.
Yeah.
Organized pages.
Organized pages.
To the left.
Yeah. Thank you. See, I learned so much from you guys. So it kind of starts with this. So someone was asking me in office hours today about majority-minority carriers. And so on the n-type side, we have the majority carriers, the n sub n's. They're basically the donor doping levels. And we have the minority carrier holes. And we have the majority carrier holes on the p side, which is basically the acceptor doping level. And we have the minority carrier electrons. So the electron density, and this is, remember, in the way it's graphed in the textbooks, this is the semi-log. So this is many orders of magnitude difference, and so that means we have a concentration gradient. And so far, at this point in the class, I had not taught you quantum mechanical tunneling yet. So the only way charge moves is drift or diffusion. And drift was, remember this is first midterm material, drift is in the presence of an electric field, and diffusion is in the presence of a concentration gradient. So here we have a huge concentration gradient that will drive this across. So, this is kind of a very staccato, very important kind of statement, but it might leave out a few details, but it's got the main gist. So, what I kind of forgot to talk about here is what's the starting point. The starting point is the concentration gradient. So concentration gradient then is assumed at that point, and that means that the carriers then diffuse across because they're trying to equilibrate the concentration gradient. But as they do so, they're creating this charge imbalance because the electrons going across are not coming for free. The electrons coming across are leaving the ionized donor, and the holes are leaving the ionized acceptor. So they're leaving behind these ionized centers. That creates an electric field, so it's going to create this dipole. The electric field opposes diffusion, and so eventually the diffusion electric field reach an equilibrium, so drift and diffusion balance each other out. So this is, do you remember on the first midterm, this is going to be a dynamic equilibrium because it's not zero, it's just they're opposing each other. For every carrier coming over to the left by diffusion, one going by drift is going to the other direction. So, and what do we end up having in the middle? It's kind of apropos because we just passed Veterans Day, which is in Europe, Armistice Day from the ending of World War I. And so this is a depletion region, so this is like no man's land, you know, between the two fronts. So here's talking about the, so in prelude to this was talking about that concentration gradient and the differences as shown there. So it's like you're opening up the floodgates. I've often given an analogy of like Panama Canal, sort of you're opening up the doors and things equilibrate. Okay, this is how Streetman presents it. They present in the NA, the ND, but you parse it together, you see this differential. So that's the key. That's the trigger point. That's the cause, and the effect is the diffusion and the depletion region. So as it diffuses and it opens up and establishing this electric field, right? We're making this dipole, and we're creating this electric field.
So you said, what was the cause and effect for that last part, last slide?
So I would argue that the cause of this is the concentration gradient, and the effect is the diffusion, which leads to the formation of the depletion region. So as they diffuse across, they create this dipole, so we get a slab of charge on either side. And because the doping is constant throughout those either side, is what we're assuming, this concentration is constant. And when I apply Poisson's equation and I integrate, constant charge ends up being linearly varying electric field, and which actually in the next diagram, or one of the next, you see the little mini booklets. This is from one of those Perea and Nudek booklets, and you can see it's actually the charge is turning into the triangle, which leads to the parabolic. So this and let's neglect these little perturbations here at the end. It's just getting a little. It's trying to be a little more scientifically accurate, that you get a skin depth effect at either end. But for now, for this class, I don't think we have to belabor that. So think of this as two slabs and a triangle. And then when you integrate the triangle, you get a parabola. So it's going to be parabolic up here. So when you have that, and here's just a reminder what the intrinsic carrier concentrations are. So then I like this. This is fairly close, fairly accurate, right? It's showing you that sail, or a different representation of the sail, but this is showing you the dynamic equilibrium. Drift and diffusion are balancing each other. The diffusion are coming driven by the concentration gradient, so there's a lot of electrons here, there's very few electrons here, so diffusion pushes it over here. But here there's an electric field, so these carriers are coming down the slope influenced by the presence of the electric field. And the holes, of course, you have to stand on your head for this, but the holes follow the same argument, but they're basically air bubbles, and they're trying to come down. So think of the hole as like a beach ball. You know, you're at the swimming pool and you're trying to push a beach ball below the surface. It takes energy, so it's the holes are gaining energies. They're going this way, so everything's inverted. It's not the presence of water; it's the presence of lack of water. It's the air inside the beach ball. Question?
So it's all kind of moving just left to right.
Which carriers are you talking about? Actually, nothing's moving. It's a net. It's a net.
They're wanting to move left to right.
Yes, yes.
And then in the conduction band, they're trying to drift left to right.
No, this is the same thing. This is the diffusion, and they got sloppy. They did not draw the drift here. Yeah, they get a little sloppy here, but it's the same story. And then remember, and this is actually midterm 1 material, that as you apply a bias, the bands tilt and lead to an electric field. So this is like launching a bowling ball down your steps, right? It's just going to go bing, 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 bing as it comes down. And so that potential energy turns into kinetic energy and accelerates. And of course, remember avalanche multiplication from the first midterm. If it distorts so much that this kinetic energy, when it hits the lattice and scatters, if it's able to impart 1/2 mv squared kinetic energy equal to or greater than the band gap energy, then you have an opportunity for a avalanche multiplication event. Okay, so this is the way Streetman draws it under equilibrium. It's dynamic equilibrium. So the carriers are moving back and forth. We've got hole diffusion, we got hole drift, we got electron diffusion, we got electron drift. Everything's like non-zero. The carriers are flying back and forth, but the net effect is zero. You pull out this multimeter and you measure across the diode, and you're not going to measure anything, right? It's going to be 0 amps because this is all happening internally and nothing else happens. So then you lead to the classic rectification, where in forward bias, you get the turn on, and in reverse, not much happens. Notice this is called generation. We'll get to that in a second. So the equations, the Poisson equation, and so forth. But in one-sided junction, yeah, this is a little better. So here we apply a bias, and we bend the bands. And so what voltage was applied to the right side? Bands go up. So therefore, of this half-dead battery, which side did I connect to the left? To the right? Sorry, you're right, my left. Negative. Right? I reduced the voltage with respect to the vacuum level, so the bands go up. Perfect. So, so the bands go up, which reveals our sail, right? The carriers in the density of states and Fermi-Dirac hasn't changed because it's still room temperature, right? So the only thing that's going to change our sail. Okay, the density of states is the bottom, and that's material dependent, so that's not going to change. And the top is the Fermi-Dirac, and that's temperature dependent, but this is, we're assuming it's the same temperature before and after. We're not changing the temperature. So this sail should be the same as it was in the equilibrium where there's no bias. So the bias pulls this up, the negative on the cathode on the N side, pulls that up, revealing these, and so those now get enhanced, which leads to your forward diffusion current. But the drift continues to motor along. This is like the tortoise and the hare, right? They just continue to motor along. They're independent of bias. Doesn't matter. They're just going to continue to run the race. And so these guys are going to be coming across. They just may not come as quickly because the electric field is smaller now. It's more diminutive. But they're still going to go across. You know, it's now going from the black diamond to the bunny slope. Right, and I think only about 2 of you get that, the Massachusetts guys. So, what is the rate limiting step for these carriers? Seven? Generation. Where? In or near? So these guys have a 50-50 chance, right, within the diffusion length, right? And then the ones here are a lost cause. They're automatically going to go to the other side. It's like it's like go to jail with no get out of jail. Was Monopoly go to jail directly? Do not pass go and collect $200. Isn't that it? So you just go directly to jail. And then these guys here. Now, thermal generation is hold on a second. Generation is a 2-carrier event, right? So I could be creating, when I create electrons, I'm also creating holes, right? But adding a few holes to this side is not really of a consequence. So it's the electrons, the minority carrier electrons. But I can also have generation happening here, pushing an electron up, and so therefore I'm creating holes near this this diffusion length. Yes, sorry.
I was just going to clarify. So generation in or near the depletion region is the rate limiting step for minority electrons?
No, because it's a bipolar device. So it's the rate limiting step for the drift. So it's electrons on the p side and holes on the n side. Yeah, you have to tabulate 4 different carrier types. Two carrier types, but 4 different current four different current components, which are illustrated right here, by the way. Waiting for it to look up. So and here's your 4 current components, by the way. So you got the diffusion, the drift, the diffusion. So these are your 4 that you have to do your accounting for. So, okay. What happens in reverse? So again, this is actually pictorially wrong. It's going to stay this because the temperature has not changed. Fermi Dirac stays the same. It's the same materials. The density state's not going to change. So this is kind of not exactly correct. I think if they drew it the normal way, they wouldn't get 0 electrons up here. So I think they took some liberties from the cartoon point of view. But the barrier lowers, and so therefore, barrier. This comes down, raising the energy barrier height. So therefore, the likelihood of carriers coming over the top is minimized. But this is the little engine that could, and so they continue to churn away. And there's this.
Does the reverse bias affect the amount of generation that happens, or just the speed at which it diffuses?
Yeah, it's the speed, because the generation is a thermally driven process. So recognize that generation's happening way over here on the left, it's happening in the middle, and it's happening over the right. It's just that I just want to emphasize the generation that's happening here in the P bulk. Those when I have a generation event here, the electron will jump up. So I'm going to add 1 extra hole to this very large hole concentration, which will be insignificant. It's going to be like 9 decimal places down the road. And adding 1 electron here, that's many diffusion lengths from here, it's going to be recombined. Because a diffusion length means, what does a diffusion length mean? So a diffusion length means what is the average distance that carrier goes before recombining. So if it's more than a diffusion length away, then it's likely to be recombined. So it's the analogy, what's the adage? It's a tree falling in the forest, no one hears it. So it basically will disappear before it can get to the junction edge.
So even though the depletion region is getting bigger, it doesn't contribute more to the current because it happens.
Well,
in
that
the
is the deviation by ideality. Yes, exactly. You're getting ahead. But yes, if it's in or near, so if it's the depletion region widens and the diffusion length stays the same, and so yes, as it comes back here, but then it's within that in the diffusion in the depletion region and within the diffusion length of criteria. So, but this opens up. Yeah. This is the conundrum. Oops. This is the conundrum about how do I have constant current going through my diode, right? I have to have Kirchhoff's current loop that's continuous, right? I can't have current just disappearing into a singularity, right? That kind of violates physics, and the only thing that's going to do that is a black hole, and even then it doesn't really disappear. So how do I have this conundrum that holes are coming in and just disappearing, and yet I have this constant current? Well, you know this because the holes coming in this way are being taken up, the torch is being taken up by the electrons coming this way. So it's a bipolar device in that I have both hole current and electron current, and they add together that the summation of them is the constant. So as you add these together, I get constant current across the junction. This is the dog tail wagging analogy where I have the minority carriers splattering across. So when I do have forward bias, I've got a large volume of electrons coming to the p side, and I have a large volume of holes coming to the n side, right? So that becomes the, and just to re-emphasize, when we started with, I'll use this one. When we started with this concentration gradient that drove everything, we were looking at the majority carriers up here. Remember, this is on a semi-log, and we're looking at the minority carriers down here. So what this, just to remind you that this dog tail wagging, we're only focusing on this and this. These we don't care about because they're majority carriers, so they don't deviate by much. So as the carriers come in, so this is NP. These are minority carriers. These are PNs, minority carriers. We're not drawing the majority carriers. So this bipolar devices, the minority carriers, usually dominates a lot of this, the rate limiting steps. And so here the carriers pile in. It builds up above the equilibrium value. And so I get a buildup of charge. And well, actually, we'll get to the temporal, but anyway, that's where that comes from. So the derivation of the ideal diode equation comes from that analysis. So you have either the charge control model or the slope of the minority carriers. And actually, Streetman does a pretty good job at that. That's this. So you're either looking at those tails. I don't like the way he draws this because he forgets to put the NP naughts here like the modular series did. Because this is not coming to 0, it's coming to NP naught. NP naught is not a 0 number, is not equal to 0. And this is coming down to PN naught. What he's drawing here is the delta. So technically he's correct, but I think that it's easier to remember it in the absolute. So you could either think of the slope of this, looking at using the diffusion equation, that you're looking at the concentration gradient, the change of carrier concentration is a function of x. That's concentration gradient, right? And so then you embed that slope into this, and you can determine the origin of the current across that interface. But I kind of like the charge control model because I guess I'm gonna be off screen there if I go there. But the charge control model is assuming that this Q, the area under the curve, is replaced every tau seconds because we're assuming recombination is happening as well. And generation recombination are just opposites of each other. So what goes up comes down. And so you tend to see, and so generation is driven by temperature up, and recombination is statistically random, but it becomes more probable when you have more carriers up there, right? It's just kind of like when the lottery a pot of money gets larger, right? You have more people buying tickets, and so the probability of a winner goes up because the whole nation's buying lottery tickets. So the more it goes up, the more faster it'll come down. But it's still statistically random, just like a lottery ticket. You still have the same probability of recombining. It's just there's more of them, so you end up having more. Is that a good analogy? Anybody buy a lottery ticket? When it was 1 billion? No. Those people aren't in class anymore, right? So I'm not going to go into the derivation of the Diode Equation on an examination, really. But there may be permutations of that, but not really that. So here's another version. Yeah, so it's just the same thing. So you end up with the Diode Equation. So it's just this exponential e to the QV over KT minus 1. And the minus 1 is this term here, which is these are based on physical parameters here. And so therefore that is the reverse leakage current. So recognize that in my diode, my minus I naught, always label axes as an engineer, this minus I naught is given by this term right here. So I can actually figure out what my reverse saturation current, or minus I naught, should be based on foreknowledge of the material parameters, because diffusion terms can probably be determined by the doping density, the minority carrier. If I know what I doped it with the majority carrier, I can certainly calculate the minority carrier knowing the intrinsic carrier concentration. And intrinsic carrier concentration is just a material parameter of the material. Diffusion length is dependent upon the doping level. I can figure that one out or even measure it. So all of those are things I can measure or ascertain fairly first principles. So when I talk about the dog tail wagging, it's kind of this is on forward bias and this is reverse bias. So here's the PN and the NP, or really the PN naught, as we were talking in class. I mean in office hours, and NP naught. So under forward bias, it goes above the equilibrium, the naughts, and under reverse bias, it goes down. And why does it go down? It's actually a good exam question. Why does it go down? Why does it get... At equilibrium, anybody into Confucius and what is it? No, Taoism, right? Keep me honest here. Isn't it Taoism in Chinese history and culture? Taoism, you have the yin and the yang, right? Yeah. So drift and diffusion is your yin and your yang, right? Under reverse bias, what happened to our diffusion current? It went in the toilet, right? It's zero, or almost zero. So therefore, but the drift is the little engine that could, keeps going. So I don't have a balance. I don't have a yin for my yang. So therefore, it sags and depresses. And you can even see it, it's within the diffusion length, right? Because it's basically hoovering up all the carriers that are near the edge, right? It's that hockey goalie crease analogy, where it's just any hockey puck within the orbit of the goalie is going to be hoovered up. Okay.
What section of the book would that be in?
That would be, we're in right around 518, so the middle of chapter 5. And then, of course, this goes back to the first midterm, but the carriers going up as a function of velocity, so as a function of electric field, they're going to accelerate and then eventually hit their saturation velocity. Okay, so let's get into reverse breakdown. Reverse breakdown, it's either Zener tunneling or avalanche breakdown, either or. It cannot be both. Zener happens right away, and it happens either one of them is going to be like this. But what is the value of this breakdown voltage? So Zener is going to happen in the first few volts because as I bend the bands, go into reverse, I can have where it's not showing the carrier densities very well, but these carriers, so remember we normally think of the holes as being, the P side as being holes, but the holes are right here. Holes are, in that case, the holes are upside down, right? And so they're like a little air bubble right here. And but below this, so these are the holes, but below this is electrons, right? It's an ocean of electrons. We've only lost a few electrons at the top, making room for the holes. So there's all these electrons even though it's the P side, it may sound a little strange, but normally these guys are not in play. They're usually so buried below the ground that they're not in play. But in this particular unusual circumstance, then this is very narrow. They can quantum mechanically tunnel across. And so, what are the conditions for tunneling? Stefan?
Availability of carriers, empty space adjacent, and a small distance.
And small distance in between, yes. So available carrier, let me repeat because I'm not sure the microphone picked it up. Available carriers, empty states adjacent, and a small distance in between. All three criteria are satisfied. And what would be the setup? How would I predict I might have small distance in between? What would be a warning sign in if I had a word problem question? What would be something?
Highly doped.
Highly doped, right? Yes, exactly. So highly doped is going to compress your depletion region and cause this to happen. So in our quantum mechanical devices, usually the preferred quantum mechanical tunneling distance is below 10 nanometers. So if this depletion region is less than 10 nanometers, 100 angstroms, then you might have some tunneling. But if you start to get wider, you start to get to a 1 micron depletion region, then probably it's not going to happen. It's going to be, yeah. And here I was trying to draw crudely the density of states. So think of it as the electrons, and then you have this little air bubble here. That's why it's kind of a crude cartoon. Now this is probably good. This is out of little z. This is showing that bowling ball analogy where it's like ping, ping, ping as it's going down the steps. And here you can see the potential energy is turning into kinetic energy, accelerating the carriers, and then it hits a scattering. And when it scatters, conservation of momentum, the carrier imparts all that energy and momentum to the lattice, sometimes causing an electron hole pair. So think of it as, your Wile E. Coyote. Remember your Bugs Bunny? Before the College of Engineering sanitized all the names of my PCs were named after Looney Tunes characters. And so Wile E. Coyote was the one that always went through the desert looking for Roadrunner. And think of it as Wile E. Coyote coming in and hitting that utility pole, right? Full bore. And then the lamppost, falls off and hits him on the head or something like that. So you've ionized the lamppost by imparting that kinetic energy. Okay, so here's kind of showing that the carrier comes in, you get an ionization, and then it creates two more particles. And here you ratchet up the voltage even more higher electric field, and now the secondary electrons can create third-party electrons and so forth. And you get this avalanche runaway. It's kind of like a nuclear reaction runaway. Questions on that? Yes?
So wait, so an electron is moving from one side to the other, but how's it creating two again?
Because it's coming down so fast and when it collides, it's going to ionize and it's going to pop an electron hole pair. It's going to pop. It's going to by delivering that kinetic energy to the lattice. It's going to knock an electron out of the valence band up the conduction band. So it's ionizing an electron, creating 3 particles out, 1 particle in. Okay. So the breakdown voltage usually follows this formality that quantum mechanical tunneling happens right away at these high doping levels, or it doesn't happen at all, and then it's going to be avalanche breakdown. And avalanche breakdown is going to be band gap dependent, right? Because the higher the band gap, the higher the voltage it can sustain, and so forth. So this is why you see wide band gaps being used for power devices. So you'll see a lot of work. We have I have a peer faculty in our department who work on silicon carbide. And so silicon carbide is great for making power switches, being able to move power around. Yes?
So like a higher band gap resists the avalanche more.
Yes, because it's higher energy needed to create that ionization event. So special cases, maybe a little less important, to be quite honest, on a short exam. But this is punch through where the depletion region goes all the way out and slams into the contact, and you get the carriers coming out. Switching dynamics. Okay, so this is more important. Junction capacitance and minority carrier storage. We already talked a little bit about minority carrier storage. Yeah, let me jump in this. So, as the depletion region is being modulated, so the capacitance is it's going to be this change in the depletion region, the small perturbation in the change in the depletion region by bias. So this is kind of showing you plus or minus. And or no, this is extending out, so it basically depleted an additional slab. So rho here, the charge density. So ND, the depletion region was pushed out a little bit, and so it added a slab here and added a slab here. So here's the delta rho. They added, so this becomes your capacitor. Delta Q over delta V is the capacitance. So this is the Q. Change in Q as a function of the small voltage, right? So that's capacitance. And so as you apply a bias, the depletion region goes from W to W plus dW, extends out, and so then you can see the depletion capacitance follows this kind of a formalism. It'll shrink under reverse because the capacitances are getting so far apart. And under forward, it gets fairly strong. And from that, of course, we could use, I think I was talking about, you could basically make a varactor diode, but we're getting ahead of ourselves a little bit. And I think we skip over this. Yeah. So you could dial in different relationships depending upon whether it's linearly graded, abrupt, or hyper-abrupt. Charge storage capacitance. So that's the time. So let's think of it in terms of turn off and turn on transients. So again, this is the buildup of the charge at the edge of the depletion region. So the current is high, so it's under forward bias. So we have greater than equilibrium values. Kind of have a very truncated board, so it's hard to draw. But I have accumulation on either side, so this is only showing you one side. And then I turn this diode off, so I go from 60 miles an hour to 0 to a dead stop, and they have this excess charge. And how is this excess charge going to disappear? Is it going to go to the other side? No, it's not going to diffuse. What?
Does it recombine?
It's going to recombine. So it's slowly recombining. So you're sitting there with your stopwatch and you're waiting for one instead of diffusion length, you think about it as recombination time. So a carrier will move in a drunkard's walk, and then it will recombine. So you could think about it as diffusion length, or how long did it take to get there, the diffusion time or whatever, the time constant to go there. So it's either the distance or the time. So when we're talking about diffusion length, we're also thinking about the average time. So one time constant, one tau, let's call this tau to be consistent, tau. So one time constant, two time constants, and eventually it should all disappear. So it'll reestablish and move back to equilibrium. Remember, Mother Nature always wants to come back to the NP naughts and the PN naughts. It wants to reestablish the equilibrium whenever a perturbation, this is a perturbation, right? I've disturbed equilibrium by forcing current through it. And then I go to 0, which is equilibrium. So everything quiets down and everything relaxes back, right? You know, it's like having a motor or so forth. You want to do some work on a motor and you unplug it from the wall. Do you go in and put your hand in right away? Probably not. You're probably going to wait a few minutes for the capacitors to discharge before the high voltage is safe enough and go in there.
It's like, what do you mean when you say it recombines?
It's recombining.
Yeah, with what?
With its... yeah, okay. So I have these majority carrier electrons, and they're splattering in here. So normally I would have 3 of these guys here, but now I got more because these have splattered over. And so where are these going to recombine with, guys? Help me here. What's this electron? His question is, where does this electron go when it recombines?
Doesn't it become part of the
The what?
It's recombined with the holes in the valence band?
Yeah, it's just going to fall down, and we have all these majority carrier holes here, so it just recombines. So, So this is maybe a little bit better representation where it's being operated as a digital switch. So I build on forward bias, I build up, and under reverse bias, it's going to fall back down, and so forth. So it's a dog tail wagging up and down, right? But we get this conundrum here where we get this large reverse current momentarily. And why do we get the reverse current? I think this guy shows it a little better. Why do we get the large reverse current? Shouldn't it be forward current? And then it's going to exponentially decay from the forward current to the reverse saturation current. Shouldn't that be the waveform? But it's not. It's large reverse current. Why? Very good test question. Stefan?
It's like temporarily reverse bias because the charge has to recombine otherwise. Like, that's not the phrase, but it's like the charge is still, there's still a bunch of excess charge at the edges of the bands, and until that goes away, the diode isn't fully in the other operating mode.
Yeah, so the diode, even though it's been flipped from forward to reverse, the diode in this Kirchhoff's voltage loop, the diode still looks as if it's in forward bias. Exactly what Stefan said, it's the minority carrier charge. So, and it's exactly the question from up front earlier, that it takes so much time for this to recombine, so it's stuck in a forward bias. So it cannot stop from being forward bias-like. The junction itself still thinks it's in forward bias, and until this is absorbed by recombination, which is exactly the earlier question, and not until it's reabsorbed can the junction then finally take on the flavor of a reverse bias. And only under reverse bias can it drop a large amount of voltage in the Kirchhoff voltage loop, right? Because a diode in reverse bias can drop a lot of voltage, but under forward bias, it doesn't because it's going up exponentially. It doesn't get very far because the current's going up, right? So it's stuck in forward bias. And at this particular point, it finally hits equilibrium, and then from here it goes from equilibrium to reverse. So the exponential is concave down in this way rather than concave up that you might expect. So, so I like the modular series booklets in this case because it's showing you the t less than 0 and the t greater than 0, where it's going back and forth, right? So it actually shows you. And here you can see its time permutations is sagging, 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 sagging. And yeah, so that's just the Streetman version. Deviations in ideality, there's several. Streetman finally added this figure. One of their latest versions. So we have deviation here, which is because what's the reverse saturation currents? The generation current in or near the depletion region. We already covered that. What happens to the depletion region as the reverse bias increases? It grows. So the volume supporting the generation current grows. So therefore, this linearly grows. What happens here when n equals 2? Well, it's the density of states. It really comes back to this that I harped on in the first midterm. This density of states is showing you that as the bands bend, I'm going to be interrogating this top, right? This is going to be moving up. So the sail is moving up, 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 up. And at first there's nothing, then there's still nothing, then there's still nothing, then there's still nothing, and then it starts to see something, and it starts to see something. So think of this as like increments of half volts, or 0.2 volts. 0.2, 0.4, 0.6, and around 0.7, boom, something starts to happen. because this is lifting this up, and so until you get to the cut-in voltage, which you learned in silicon circuits is 0.7 volts, the diffusion current hasn't really kicked in. That's what normally happens. That's the ideal case. So before the diffusion current kicks in, you simply have generation recombination. It's kind of, which is a two-carrier event. Generation recombination has, electron recombining with the holes, two carriers. So therefore, ideality factor is 2. High-level injection is now you're racing with so many carriers are racing across the junction because your absolute current is getting so high that they're now colliding with each other as they're coming across. I was trying to think of a movie analogy there. Where is there like two armies like hitting and they're just like colliding? So I don't know. Maybe it's when the doors of Mordor open up. And then you get the ohmic effects where it rolls over. That's where, so then in the ohmic effects, what I mean there is that's where the other parts, so here we're normally worried about what happens in here in the depletion region, W. But now the ohmic effects means that I have a resistor there, and a resistor there, and a resistor there, and a resistor there. So this is going to be the resistance of the contact, and the bulk, and the bulk. So I get this lumped element. And so what's happening in the diode itself is less important. It's these parasitics are now expressing themselves more fully because the absolute current gets up and it rolls over. And with these resistances, remember, these are getting I squared R joule heating, so then your device actually gets hot, and eventually it actually burns and blows up. Okay. So those are the deviations from ideality. Also kind of embedded in there is the idea that you can't go past the diode itself, can't go past the flat band condition. The cut-in voltage also is going to be a function of band gap. This is the question that was happening earlier about the recombination generation. So remember, that's happening everywhere. It's only the ones in or near that really count. But we do have generation recombination at the extreme ends. And so it's just what's up comes down. If there's a recombination center or trap, they contribute and they enhance the recombination generation. And generation, depletion region, ohmic losses. Okay, special cases, less important, but you can do the linear graded junctions. But now this is important, metal semiconductor junctions and ohmic contacts. So you start off with the work function for the metal, work function for the semiconductor, and then you line it all up with the vacuum level. And so this is how they align based on these. These are numbers given to you, or you experimentally determine them. And then you know where the conduction band is relative to the Fermi level because you know the doping level. So you can calculate the difference there through the equations you've been given. And so this is the metal, and this is the semiconductor. I plug them together, and in the ideal case, it's as if these two, the valence band and conduction band, get super glued, and they connect right here. And therefore, I end up with the Schottky barrier height. So this is a barrier inhibiting for the carrier electrons coming this way. And this is a barrier inhibiting the electrons coming this way. It is a majority carrier device. There's electrons and electrons, and there's no holes. What's this positive sign here? I just told you there's no holes. What's this positive sign? Connor.
I think it's they're like
Does he?
Is it intrinsic?
No, not intrinsic. On the right track. It's depletion. So this is the ionized donors, right? It's depletion region. So the band bending is always representative of charge and electric field, right? So if it's tilting, it's electric field. If it's bending, there's charge. Where did that charge come from? It's the ionized donors, because this is just a metal semiconductor junction. Right. So I end up with this depletion region. So all the electrons are swept away, revealing the ionized donors. So the positive charge associated with that pushes this down with respect to the metal. So then the bands distort and bend and establish equilibrium, and the Fermi levels align. And when the Fermi levels align, it's representative that I have established a dynamic equilibrium, because the carriers are going to be doing the diffusion thing and the drift thing, just like we talked about before, but they're going to balance each other out. So the holes, the P side is the same thing. I have a work function specified by this, the semiconductor work function, the metal work function, and I parse those together, superglue those, and the holes wanting to come from this P-type material have to come across this barrier, and so this barrier is non-trivial, and so it inhibits and holds back the holes there, and the metal is electron rich, and I still have a Schottky barrier height that inhibits the flow of electrons this way. So I don't really readily have holes going this way. I don't have electrons going this way. So I have low current, no current. But under forward bias, the barrier lowers. I get forward bias. On reverse bias, the barrier increases, and the Schottky barrier height still continues to block or inhibit the backflow of carriers. That's going in the opposite direction, right? Because I want electrons to go from here to here, and the electrons going there is in the opposite direction. That would manifest as a reverse current. Okay, so then in practical junctions, I get the metal and the semiconductor. I'll lock those guys together, and I actually get the, I guess I was glossing over this, but remember in class I talked about what is the degree of freedom. So think of it this way. I kind of glossed over this in the last one, but let's play it all the way out here. You should be able to rationalize this out using the vocabulary and the physics that we've taught. So or I've taught. I guess I'm a colleague with Streetman and Banerjee in this case. So then the metal here has a higher energy with respect to the Fermi level of the semiconductor, right? So therefore, the metal either has to lower with respect to the semiconductor to bring it into balance, into equilibrium, but the metal's metal. It's not going anywhere. It's loaded with electrons. It's like trying to take a bucket of water out of the ocean. You know, sea level is still going to be sea level. You're not going to change it. It's too much electrons. So that's not going. That's going to be rock steady. So the semiconductor has to then come up with respect to the metal. Okay, so that's what I got to do. How do I take a semiconductor up? Well, then let's rationalize it. So to put a Fermi level and a semiconductor higher means that the surface is becoming electron rich, right? It's becoming, to go up means it's becoming more full of electrons, and it's an N-type material. So how does an N-type material become more full of electrons? I accumulate electrons, which are majority carrier, to the surface, the bands bend, and I have lots of electrons to corral because it's the majority carrier and there are plenty of them, and they pile up within a skin depth. Right. You can think of it, rationalize it out the same way with the holes. I need to lower the holes with respect to the electrons, so the only way I can lower the holes, the Fermi level of the p side, is to accumulate holes. So holes push everything down. and I get this very small. Practical, real-world metal semiconductors, we actually get Fermi-level pinning, where you get traps and defects, and sometimes the density of states associated with that is so high that the Fermi level pierces that recombination, that trap level, and it pins the Fermi level. The terminology we use in our field is that it pins the Fermi level, so that no matter what you do with N-type gallium arsenide, you get a 0.8 electron volt Schottky barrier height, no matter what you do. Indium arsenide is actually more forgiving, that no matter what you do, the Fermi level pins in that way, and so therefore for electrons to flow, there's really no appreciable barrier there. Hetero junctions, this is the fun stuff. Now we can make our quantum wells and everything. So more layers, combining two or more layers of different band gaps. And so it's the same thing. You have the work functions and the electron affinities. You line them all up. They have an energy band difference, band gap difference, and so they manifest often as 2/3, 1/3, or 70/30, 60/40, 70/30. And so then you end up with the band offsets. And so we get this beautiful heterojunction where holes going this way are not so blocked, but electrons coming this way are very much blocked. And if we get to bipolar junction transistors, you'll see the beauty in that, where I can manipulate one carrier versus the other. This is the origin of the, no, let me go to another figure. This is the origin of the MOSFET we talked about briefly today. So at a heterojunction, I get this interface, I get this discontinuity, and here's the Fermi level, right? Fermi level is showing me the probability of occupancy is 0.5%. So what happens when the conduction band goes below the Fermi level? Fermi level is above the conduction band. What do you think's happening there? It's getting its feet wet, right? It's getting its feet wet with electrons. It's below the water mark. This is the ocean. This is sea level in the ocean. So if it goes below, it's getting its feet wet, right? So therefore, this is filled with carriers. That quantum well, the first quantum well, is filled with carriers. So I have a sheet of carriers, and this is where you get the value that I get the large mobility into the board. So this quantum well is into the board. So the source would be here, the drain would be on the back side of the screen, and the gate would be here, pulling this up. It'd be like taking a rug. It'd be like taking, a rug in a hallway. You lift it up, and so you would lift this up, and this would come up out of the water and empty of charge. This is how a MOSFET works, and then you lower it back down. So you're adding and subtracting charge in the channel by lowering this down. That's how a MOSFET works. And then the last thing is the ionized impurity scattering is minimal because the dopants are here and they modulation dope by, they basically transfer. They're basically, the electrons are bouncing around through kT kinetic energy, and they're trying to find the global minimum. Where's the global minimum? Right here. So, what's your question?
You say we're looking at it like from the side? Is that like the
Yeah, I would. This would be. I would epitaxially grow this. This would be the substrate, and then I would deposit a layer of gallium arsenide, lightly doped. I would put a spacer on undoped aluminum gallium arsenide, and then I would grow highly doped aluminum gallium arsenide, and I would have my contact out here. Probably I'd just another intrinsic layer, but that's getting too complicated. And I put my gate up here, and so yeah, this would be the top. Yeah. Okay. Yeah, I used to grow an indium phosphide version of this to pay the bills in graduate school. I grew MOSFETs for one of the satellite communication companies. So there's probably a lot of these MOSFETs, at least back once upon a time, in Earth's orbit that I grew. I guess that's it for this slide deck. applications. So what are our applications? There's going to be some digital switches, some microwave switches, some optical detectors and optical emitters, right? So we have rectifiers. So that's kind of in the digital regime. So an ideal diode, I want to have a short in the forward and open in the reverse. So therefore, I want this to be completely, open. So to reduce the reverse leakage current, I might use a wide band gap, which lowers the intrinsic carrier concentration, which lowers the opportunity for generation to happen. Reduce power losses, where it rolls over the ohmic losses. I want to make the device very large. That reduces the I squared R joule heating by reducing the resistance, right? A highly doped contact on top. I want high breakdown voltage, so I want wide bandgap material also there for that reason. High critical field. Maybe use a one-sided junction where the more lightly doped side is governs the breakdown, so that make that lightly doped. Switching diodes, if you understood what we were talking about with the dogtail wagging, now you understand that the rate limiting step is the recombination. Carriers, when it builds up, the only way to get rid of the carriers down is to just sit there. There's not much you can do. You just have to sit and wait for recombination to happen. So if I add recombination centers, I can accelerate that recombination rate. So if I want to make a fast switching diode, I actually use, sometimes I might want to use poor quality semiconductor material on purpose. So sometimes good material is not always what you want. Here it kills the carrier lifetime, so things are recombination. Now this would be a lousy laser, right? Lousy LED, but for a fast switch, I want to do something in the terahertz, maybe this will work. Make lightly doped neutral region shorter than minority carrier diffusion length. So a narrow base diode, what's that all about? It's kind of a smaller point, but in this dogtail wagging scenario, think of it as the surface of the semiconductor, the contact is here. So normally this would be the Gaussian distribution. And I put the contact here, so it basically means that the boundary condition, by putting my contact here, so the semiconductor does not go all the way continuously here. It just stops here, and this is the surface of the semiconductor. So it makes a boundary condition. So instead of going this way, it's got to come down and go to zero at the surface. So I basically got rid of all this charge. So I kind of like, cheated a little bit. And so that's what I mean, a short-based, narrow-based diode here. Breakdown voltage. We talked a little bit about that. So you can tailor it by the doping, whether it's going to be Zener or Avalanche, and you can change the voltage capacitance relationships based on whether it's abrupt, linearly graded. So I can tailor all of that. Fun stuff is, okay, the only thing I'm warning you, I gave you a lot of eye candy on the tunnel diodes because it's an area of research in my group. But the only part that's testable is 10.1 from Streetman, which is the Esaki tunnel diode. So I was just kind of showing you the things we do. So really understand this band diagram from my book chapter. So this is maybe even better than Streetman's textbook. It shows you beautifully the sails. Zero bias, here's the carriers, here's the keyholes lining up, and you get the probability for tunneling. You have available carriers, you have empty states, and a small distance in between, quantum mechanically tunneling, and so that tunneling current goes up, and then the keyholes detune, tunneling current goes down, and then eventually you get the forward bias diffusion current like a normal diode. And what do you get in reverse? I get immediate Zener. Immediate Zener. I get these carriers coming over. Actually, it's not the holes. It's actually these electrons here. These electrons coming over. Okay, so that's all you need to know about tunnel diodes formally. Hopefully you take a little bit of an interest and see some of the other stuff, but that's only outside the classroom. Yeah, so this is showing you some stuff. Yeah, we just submitted a paper on one of these actually just yesterday, I think. My team member. Yeah, in the good old. So I don't know where he is right now because he retired, but I wanted to send him an advanced manuscript because I think he'd be tickled by some of the things we're discovering with his devices. Completely unexpected. So let's fast forward past all this. Solar cells. They operate in the fourth quadrant, so it's power delivered, right? And just remember the fundamentals. So, I have diode, and the generation current is happening. The drift current, the reverse saturation current, is happening by the drift current component, which is the generation in or near the depletion region. So what happens if I photopump this, shine a laser onto my junction? I'm going to, as I ratchet up the current, the illumination, the diode should go down. And with that, I will get an open circuit voltage and a short circuit current. And I can take power delivered is going to be V maximum and I maximum. Power delivered. So this is power delivered because it's positive voltage and negative current. So the power absorbed is negative, which means power is delivered. And so you can see the different efficiencies. Did I update this? It's reasonably, it's 2018. Yeah, I think that's February 2018. So this is reasonably up to date from the National Renewable Energy Lab. All the different solar cell technologies. What's the rover on Mars that apparently went to sleep and they think it might have died? I don't know what solar cell they would use for that, because usually in space applications, like we're driving a communication satellite, you need a lot of power. So you're going to use something like these triple junction tandem solar cells for a lot of power delivery, where cost is not an object because the satellite shares, over time usage, and so it's a shared cost. But on the surface of Mars, actually, I don't know what you would use, whether you would use silicon or not. So any of these can actually work as a solar cell, but it's just what is the, where's the light? This is the air mass in outer space. This is the light in outer space with zero air mass. This is the light at North America, where it's coming in at obliquely at 1.5. Air mass 1.0 is on the equator, and you get the little dips and everything. So this is showing you how a silicon solar cell, so this is the cutoff wavelength. So this is showing you that most of the light is absorbed. So silicon is actually a very good absorber for solar cells. And of course the light is being attenuated, the photon flux, it's being attenuated, it's going deeper and deeper. So it's the surface that's really contributing to the absorption. And here's what I drew on the board, right? Maybe a better rendition. It's moving down, 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 down. And so that's a solar cell, that's a photodiode, and that's a diode. Or no, that's a LED or a laser maybe. So this is more or less how we build it. Is any of you registered for my 5237 class? No, none of you. Oh, one of you. Okay, so yeah, it's the solar cell lab class that we're gonna Professor Tyler Grassman and I offer next spring semester. It's already full. Apparently, we already filled up both sections. I finally lobbied for 2 sections this year instead of 1, or 2 sections next year, and so they filled up very quickly. So here's the way those are made. You know, you screen print perhaps with that, and so here you have the silicon. It's basically a PN junction. Yeah, here's the maximum power. So the solar cell people, they usually flip this. That's the way they tend to look at it, but a lot of the solar cell people came from the 60s, so they like to flip things. So here's the VOC and the short circuit, and here's the maximum power delivered. So this is wasted power. So, and here's the light coming in, leading to spontaneous emission. And here's the recombination, leading to this is an absorption, this is a spontaneous emission, and this is a stimulated emission, where this photon comes in, stimulates this reabsorption. So this second photon is in coherence with the first. So this is the basis of a laser. Yeah, this is just the equivalent circuit model of a solar cell, so it's really a diode, and it can deliver power to a load. And yeah, here's the International Space Station. It's been a long time since I looked up in the sky. Did anybody ever look in the sky and actually see that white blip go across? You can actually see, if you know where to look and when to look, you can actually see it's brighter than a meteor. You can see this. Of course, you have to see it before sunrise and after sunset, because in the middle of the night there's no sun to reflect off because you're on the dark side of the Earth, right? So you usually, but you can see this from Earth with your naked eye. You don't need binoculars or anything. How do you know you got a satellite? How do you know you're seeing a satellite versus a meteor? Any of you amateur astronomers? I was reminded when I went back to visit my old prep school yesterday in Massachusetts that I used to run the telescope on the top of the science building, and we had this big telescope that the Navy used to use to monitor satellites. So how do you know the difference between a meteor and a satellite?
Doesn't the satellite just follow the consistent path?
Yeah, it's going to stay the same brightness until it goes into the shadow of the Earth. So it's going to be very constant. And the meteor, yes, it's going to increase in brightness as it enters the Earth's atmosphere, and then it's going to dim down as it breaks apart and burns up. So exactly right. Yeah. But this will be fairly constant. So this is like, oh, by the way, I should put a plug in. I think it's almost official. Our service learning course, I'm going to take a group of 18 students who are interested. We're going to take them to Tanzania in May of 2019, if you're interested. We'll be opening up a second half of spring semester class, and then for 1 credit. Like after spring break to the end, just 1 credit hour to do the warm-up, the preparation, and then 3 credit hours in May to go to Tanzania. So we're not going to install something as aggressive as this. We're just trying to put some solar panels on some dormitories at an orphanage in Tanzania. So stay tuned for that. This is as a solar cell is either made badly or gets old. It will walk from this ideal condition, and it'll start to get a shunt, this is a series resistance, but also you can get a shunt resistance down here, shunt current, and either way it's attenuating. So therefore you're losing power as in that condition. No, so you want to get as many electron hole pairs created. So you want the light, every photon to come in to create, and so you want it to ricochet around. So the texturing allows it to ricochet around. Or you're using, using mirrors and stuff, perhaps. Here's the triple junctions monolithic tandem solar cell. So of course we have to belabor all the lattice matching as we go from all these different material systems. So I have to worry about exceeding exceeding the critical thickness and creating misfit dislocations. And so here's as you're ratcheting up the power from 1 sun to 10 suns to 100 suns to 1,000 suns. If you want to use this in a concentration mode where you're shining a big parabolic mirror onto your expensive solar cell, your VOC can go up, your efficiency can go up, but also, of course, the heat goes up. So you got to water cool these usually. Here's just a quick exposure to what we're learning in my 5833 organic class, organic and printed electronics class. This is the solutions we make from the plastics, turn into printable solutions, and make things like this, plasmonics. Anyway, photodetectors. That's where we want raw speed. So we want photodetectors to be launching into optical fibers. And so here's a photoconductor. The light comes in and it's going to create electron hole pairs. So the conductivity from this ohmic contact to that will change. So I can measure resistance. But that's not what the solar cell people use. I mean, the telecom people use. The telecom people use something more like this. It's going to be a PIN, where the carriers are generated in the I region and nominally undoped, and they're going to be swept out. Here's the absorption. It's going to be towards the surface. And so as the wavelength goes smaller, as the energy goes up, this is going to move closer to the surface. And that's why you see this cutoff. So this cutoff is associated with, Stefan.
Are PINs usually heterojunctions right now?
They're usually heterojunctions, yes, because I want to get I want the P and N to be, or one of them, to act as a window so the light can come in and out. Yes, yeah, exactly. So this is the band gap cutoff. So the photons are now too long wavelength means small energy, and so therefore these are unable to kick an electron from the valence band to the conduction band. And then here is because the absorption is getting higher and higher and higher, and therefore it's getting absorbed more close to the surface, and when it gets closer to the surface it gets recombination due to the dangling bonds at the surface. And why does silicon and where's germanium? Germanium. Why does silicon and germanium have the shoulder and the others have an abrupt cutoff? Yes.
Isn't it the direct and indirect band gaps?
Yes. So which is which?
The drop-off's direct.
Yes. And so why is the indirect beam have a shoulder?
Because there's
So like K has to change, doesn't it?
Yeah, the momentum vector K has to change, and how is it changing? What additional particle is participating? I'm giving it away. A phonon, which is quantized vibrational energy, which is basically heat. So a phonon has to participate to keep the momentum vector, right, as it comes across. So it smears the edge. It smears the edge, so I can have either absorption of a phonon or emission of a phonon. So it sort of creates a shoulder, smears out the demarcation of the edge.
So wait, so the phonon could either be absorbed or released to
Yeah.
keep the momentum constant?
Yes.
Okay.
Yeah, you really get fancy separate absorption and multiplication, where you have absorption, and this gets low noise. This is not unlike some things I used to grow back in my old Michigan days. In fact, this is a figure from my PhD advisor's textbook, I think. I think this is not treatment. I think this is, or no, maybe that's treatment. But it's not unlike some of the things I made. Yeah, this is what I made. Reduced capacitance with MSM, so you're using Schottky barriers. And so Schottky barriers to evaporate. So I actually don't need a p-n junction. You could actually make an MSM on a undoped material, some exotic new semiconductor that you made and you haven't figured out how to dope it p-type or n-type. You could make an MSM photodiode. So it's just, all you need is Schottky barriers. But that's kind of a little eye candy for you. Do you know why the sunset is red? No one should graduate from my class if you don't know why the sunset is red. And here's your dispersion correcting fiber, or actually dispersion-less fiber. And here's your normal old school fiber, graded index, where the ray tracing causes the corruption of the signal. And here you can see. And so here's the dB, the attenuation of the fused silica. So usually you're operating at 1.55 microns. And remember, the innovations came from wavelength division multiplexing, putting like 8 to 10 channels all in one fiber. Erbium doped fiber amplifiers, being able to optically pump and boost the signal. And dispersion correcting fiber is being able to correct for being able to put something even more aggressive. It kind of folds back and does the inverse. It's like an inverse Fourier transform of this, and so it brings it back to restores it back to its original signal. But in other words, you don't have to dig up the entire fiber optic grid all across the United States to put the new fiber in. You can just splice in small little units. So it's very labor, saves a lot of labor. So here's your Pink Floyd cover art for wavelength division multiplexing. Here's how you photo pump it with a 980 pump laser, and then you get the stimulated emission. The photon comes in, and you get 2 photons out, stimulated emission, relaxing from the E2 to the E1. Here's the where it comes in, boosted signal, and here's the dispersion. And yeah, this is just a little eye candy of some of the things, integrated photoreceivers that I did. I think this took 12 mask levels or so. This is probably the most complicated circuit that I did. Light emission, fundamentals, including band gap. So, right, band gap tells you which color you're going to be. Band gap wavelength is on the right, which you might not have noticed. And so here's I can hit all the different colors based on the selection of band gap. And so if I want to make a red LED or so, wait, is this red? Yeah, so this is gallium arsenide. So if I want to push it into a red LED, actually that's another class you might want to consider. If you got squeezed out of the solar cell lab, I'm hoping to work with a colleague to redesign the 5037 lab class offered next fall. Who's going to be here next fall? Okay. Some of you are fifth-year seniors? Okay. So that class, I'm hoping to reinvent it to maybe build a red LED. It's got to be red, right, for it's Ohio State. and maybe a block O, I don't know. That might be a little more complicated. But a red LED, and then those high electron mobility transistors I was talking about today, you might get a chance to make a HEMT in class. So here's an LED as you go through the evolutions of the lumens per watt, wall plug efficiency as they get better and better. They get better optical engineering, better symmetric quality. Right, this gets a little beyond. I did want to expose you to the OLEDs that came out that are populated on our cell phones now. So this is the small molecule version here, Qingtang, and this is the organic polymer one. This is, remember, Richard Friend. I think both of these guys are probably on a short list for a future Nobel Prize. And I did a sabbatical at his startup company. So here's the early version of an OLED, the LQ3. This emits in the green. And this is a little eye candy, pun intended. So here's the beauty of the quantum well. You guys voted me down for a second take-home problem, but I was going to have you design a quantum well to get a specific wavelength of light, a 980 nanometer laser, and I was going to have you tell me which semiconductor material and what is the width of the quantum well to get the energy levels such that I'm going to exactly get a 980 nanometer photon emitted. So you dodged a bullet. So if the quantum well is very sloppy, we get a three-dimensional confinement, and carriers are scattered all over 1.8 kT. But if you shrink it, it's going to be very well defined, very singular wavelength. You can do all this lens shaping and optical emission and texturing and things like that. This is courtesy of Fred Schubert, my former colleague at Bell Labs. But lasers, the other half, this is the finish line, right? So we want to drive these lasers and hit these bits, and so here. So here's the spontaneous emission. So when I forward bias the PN junction, the carriers are recombining, and they're going to reabsorb and emit photons near the band gap. But there's going to be sort of a Gaussian distribution. So the wavelengths will be a little bit, smeared by a Gaussian distribution. So, but I'm going to put this into a laser cavity with well-defined mirrors, which will then say I have certain modes supported. So these are going to be the wavelengths that are actually supported. So if I send this laser diode through a spectrometer, I'm going to measure these different wavelengths on my spectrometer. It's unfortunate that the photonics lab, which I sometimes used to teach, it's unfortunate it got canceled, because this is one of the measurements you would have done. So as a laser goes from below threshold to above threshold, then it starts to laze and you'll see the modes kick in. But below threshold, it actually looks like a LED. Just sort of a Gaussian distribution of light. And so here's how you can... So now in a laser, you're not only making quantum wells and trying to define the wavelength, but you're also going to start to optically engineer things where I want to make a well-defined beam, because I got to get that beam into an optical fiber, and that's not easy. That's like Luke Skywalker trying to hit the torpedo through and blow up the Death Star, right? I have a very small little window to get that photon, or was it a photon? Or I'm mixing metaphors here, Star Trek and Star Wars. But here I can do shape engineering of the beam coming out. And so therefore it's easier to focus and launch in, more power. And here I can get more power out, and so forth. But to get the really, more complicated, I'm going to do carrier confinement and optical waveguiding. I've got to consider both the carrier, the electrons and holes, but I also have to consider the photons being waveguided in the laser. So yeah, here's the energy levels, and therefore these are the ones that are in play for that particular to create the the emitted wavelengths. And here you can boost your efficiency by creating multiple quantum wells. And here the gradients will select individual wavelengths and destructively interfere with the others. And then I get into the two-dimensional. I was just kind of showing you why I might want to make a quantum dot laser. So the density of states I now can have very precisely defined. Okay, so that's pretty much it. I think there's one last slide showing, yeah. So some of this stuff, okay. Anyway, questions? Yes?
Can you go back to the deviations from ideality?
Yes.
And explain that n equals 2 section one more time.
There's actually two n equals 2 regions. This is n equals 2, and this is n equals 2. So this is because the forward bias diffusion current has not kicked in. So this is kind of acting still like a reverse bias diode, because I erased it, but the sail has not revealed itself over the potential energy barrier. So there's very little diffusion current. This drift is still happening. So it's really kind of recombination generation, just like a reverse bias diode, is still taking place. So it really doesn't, the diode does not start at 0, it starts here really. And so this is dominated by generation recombination. And this is the high level injection where so much carrier is coming across. But this is just intrinsic. N equals 2 is always happening. N equals 2 is happening in reverse. N equals 2 is happening here. And N equals 2 is happening here. It's just that it's now overwhelmed. So this is really 1 point. So a silicon diode has an ideality factor of 1.02, because what is it? Then that would make it 2% is recombination generation. The other 98% is the diffusion current.
So the diffusion can cause forward current as well as reverse current? Or not the drift, sorry.
Drift is happening. Yeah, that's the point. Is drift is happening. The generation recombination in or near the depletion region is happening reverse and forward. It's happening all the time. It's happening everywhere, and it's happening all the time. It's just whether it's overwhelmed and masks. You know, here the diffusion current is so much larger that that this is now overwhelmed and masked. Oh, and here it's now becoming such a large component. But normally it's hidden in the noise. Okay. Okay, so it looks like people are running out of questions. There's a long pregnant pause there. Use the theater term. So tomorrow is supposed to be a nasty weather day. I'm probably going to work from home and create a pile of papers, create a pile of peer review proposals. But I'll be, Friday will be a normal lecture day. You can challenge me there. I probably won't be answering too many emails tomorrow because I got to finally focus on this overdue project. But the Friday and the weekend, and then the exams first thing Monday morning. But compose your questions. Hit me up with that on Friday, and we can discuss.
So, recombination is just when the hole in the electron.
Yes. Yep.
They just cancel each other out.
Yeah, they can. Yeah. Okay. You good? It's clear as mud. Oh, question.
Could you go back to the picture of the ECE tunnel diode?
Oh. Yes. Right. Yes.
Yeah, so in that picture, it looks like the location or the electron probability function is moving, but you said earlier that the Fermi function and the density of states do not change very
Yeah, the green is not changing because it's still room temperature. So this is the same. The green is the same. It's supposed to be the same every pictogram.
What about the red then?
The red should be the same too. Yeah, because KT is KT.
So what is changing?
Simply the bias, so it's just opening and closing the keyhole. And remember, actually, that I know this is a highly, to be qualified as an ECE, it's highly doped junction, kind of like the Zener. But in a normal diode, recognize that let me be right-handed here. That the depletion region not only goes, forward and reverse, up and down, but the depletion region actually goes, it gets. Let me see how to do that. As it goes into reverse, it grows apart, right? It's going like that, right? As you go far, larger and a normal diode under a reverse bias, it's I'm not gesticulating very well. Oops. But it's gone from forward, so it's tight. The depletion region is narrow, right? And then it's going to go into reverse, and it's not only going to go down, but it's also going to go apart. Remember? So it kind of comes in and comes out, comes in, comes out. But the Fermi function and density of states, that's not changing.
So is the variation in the condition on that hump in the diode equation for the tunnel diode, is that due to the widening of or the shrinking of the depletion region then? Because when you say, and in that diagram, it seems like when you say like fitting the keyhole, it's that the energy states of because the three conditions for tunneling.
Yes.
If it's available carriers, available empty states, and a small distance in between.
Mm-hmm.
But you said earlier that the Fermi function and the density of states do not change. So, and that flag doesn't change.
Yeah.
Is that not? Is it not changing in this case as well?
Yeah. Yes, correct. The green and the reds are not changing.
So then the only thing that is changing is the size of the depletion region and
No, the overlap. So the criteria was the empty states opposite. So here's empty states, but they're not opposite. They're above.
Ah, I see. Okay.
Here they're opposite. That's above and that's below. So tunneling current that's the tunneling current. It goes up the keyhole lines, it detunes. The diffusion current that we learned about has a cut-in voltage here, V cut-in. And then the tunnel diode is the aggregate of those two current components. This is your normal diffusion, and this is your tunneling. The tunneling only creates this camel hump. Yes?
It doesn't create the hump in reverse, right? It just drops down.
For an Asaki, it goes like this. For an RTD, actually, it's a symmetric. It doesn't matter whether you go this way or that way. It actually manifests, a true RTD is symmetric. You get an NDR in reverse too. Unless you want to talk about these wonky things that we're publishing on now. These are not symmetric. This thing comes and it's a mess. It's a complete mess. This is what my talk was on at MIT Lincoln Labs yesterday. Okay. Questions? Okay. So I will see you on Monday. I'm sorry, Friday morning, and the exam is on Monday, and so I may hide under a rock tomorrow to get my my stack of work graded, and hiding from the sleet and so forth. So stay safe out there. Any of you have to drive to campus tomorrow because the roads will be nasty. And Ohioans do not know how to drive in the snow. In Finland, you actually, to get your driver's license in Finland, because it's so snowy, to complete your driver's examination, you have to go on a frozen lake and do a figure eight under control through those cones. And if you can't, with the control, go through the cones, you don't pass. So the best drivers in the world, in my opinion, are Finnish drivers because they can drive under any conditions. Okay. Be safe. See you on Friday.
Wait. What if they don't know how to drive ECE? Where it's not all.
I think that would be easy.
Probably not.